10702 or 36702. If you're in CS, you'll probably want to sign up as 10702. If you're in statistics, 36702. Do me a favor, if you're auditing the class, go to your department and fill out an audit form. It's better for us to have a count how many people are attending. Okay, and if you're not here for 702, this is your chance to go somewhere else and find a class. For those of you who just walked in, there's a syllabus, which I'll tell you what, at this point, I'm going to leave extra syllabuses up here and over here. You can just grab one. Hopefully don't run out of seats. It doesn't matter if you have one anyway, because I'm going to tell you what's in it and it's on the front page. All right, that is Ryan and Tim Sharani, and I am Larry Wasserman. We're co-teaching this course. We're both from statistics. There's two TAs. Matt is sitting right here, and Jeff. Oh, there he is. Okay, I was worried he didn't show up. And Jeff's back there. Right, so now you know all the important people here. And the goal today is to tell you what's in the syllabus. You can follow along, and then we're going to start. Generally, we start right at 1:30, and one of the course policies is we try to do the most important thing in the first 2 minutes. So if you're late, sorry, I missed one. So you're really on that time. Let me tell you what the website is. It's www. So there'll be there's going to be lecture notes handed out for some of the lectures, book chapters, things like that. You can find them there. Syllabus is there if you didn't get one. Updates, test information, whatever. Okay, everything is there. For those of you who just came in, there's some extra syllabuses. Are there any still? There's a few up here and a few up there. And there's still some seats. Okay, and what's going to happen is Ryan and I will teach roughly about half of the classes each. And there's a tentative schedule of what topics we're covering on the website, although of course that might change as we go along and we'll see how things go and so on. So let me tell you a bit about the course, and then I'll see if Ryan wants to add anything. This is supposed to be a second graduate course in machine learning, statistical machine learning. It's an advanced course. We assume you've taken 701, which is the first machine learning course, and we also assume you've taken 36705, which is intermediate statistical theory. If you want to take this course and you have not taken the prerequisites, that's fine with us. However, the burden is on you to make sure you make up whatever background material you need to take the course. So we're going to assume you know the stuff in those courses, and if you feel like you can take the course without taking those courses first, just make sure you find out what was in those courses and download the material and study it and so on, because we will assume you're familiar with basic things from those courses. For example, you should know things like what is convergence and probability, what's the central limit theorem, what is maximum likelihood, what is regression, what's a classifier, what is bias variance trade-off. I hope all those terms kind of sound familiar. So again, if they don't, you might find the course a bit rough, and if you feel like you need a refresher course, you should probably go back to the notes from those courses 701 and 705, which are probably available online, and review that material. Because we are going to assume, again, that you have seen that stuff before. Some of the topics we'll cover are things you've done in 701. The difference is we're going to do them in more detail, and in particular with more attention to what the theoretical background is for these things. So we kind of go into more depth on these topics. All right, so in the syllabus, it describes the course, It introduces us, as already pointed out, the four of us are Ryan, Jeff, and Matt, and also there's our contact information. The course secretary is Mary Alice McShane, and she's in Baker Hall. We have 4 different office hours, which have, actually I have to tell you that since I printed this, they've changed. So look on the syllabus because the office hours are a bit different. Ryan's are still Mondays, mine are still Wednesdays. Jeff, I think, changed his. Jeff to 3:30 on Thursday, is that right? And Matt's going to be 4:30 on Thursdays. And Thursdays is a great day because homework's always going to be due Fridays at 3 o'clock. And I know people tend to leave things at the last minute, although I'm not recommending that. So having office hours for the TAs on Thursdays is probably going to be very helpful for you. All right, and of course you can always make appointments with us by just send us an email if you need to meet with us. The textbook is Statistical Machine Learning by myself and Han Liu. It is still in progress, unfortunately. But we will be posting stuff for you on the website that you can download, PDF files and so on. So in particular, one thing you should do after class today is go to the website, and there's already 2 files up there. One is called Review, which I'm going to go through in a few minutes, which is just a very quick review of basics like regression and maximum likelihood. And then there's the first topic, which is non-parametric density estimation. So those notes are already posted, and I recommend you print them out actually and bring them to class with you. Then you don't have to take notes. And having a printout is good. I mean, you guys are always doing stuff on the screen, so if you want to look at it on the screen, that's fine. But if you print it out, you can write stuff next to it. I guess you could probably have ways of doing that on the computer, I don't know. But I would bring a printout of the notes if I was you, and then you can write down notes, extra notes as you go. So when we have gems of wisdom, you know, that you remember on the spot, you might want to write them down next to the notes that you have. There are other books that are useful, but don't quite cover the same stuff. In fact, there really isn't a good book on sort of theoretical machine learning. So a lot of the stuff we're going to talk about isn't necessarily covered in standard texts. So there's a list of other textbooks you might find useful. There's going to be 5 assignments. They're always due Friday at 3 o'clock, which means you have to bring them to Mary Alice's office and hand them to her. If she's not there, put the time on your assignment slide under the door. Okay? If you need an extension for some reason, you're sick or you have a conference that day, that's fine as long as you let us know ahead of time. Don't 2 days later say, oh, I never handed in the assignment, can I get an extension? But if you tell us ahead of time, I need an extension for the following reason, then that's fine. We can often give you an extension for any reasonable reason. Okay. You're welcome to work together on homeworks. In fact, it's probably a good thing. But when you go to do your write-up, when you finally go to write up your solutions to hand in, we expect you'll do your own write-up separately, and you should also put on top who you work with. Okay? But working together is fine otherwise. There'll be a midterm exam Wednesday, March 5th. And there's a project which we'll get to in a minute. And the grading is 50% assignments, 25% midterm, 25% audit. There's going to be some programming we have to do. It's not a programming course, but of course we use the computer. Most common things people use in this course are MATLAB and R. I always try to be a little bit evangelical and convince you to use R. It always starts out that everybody wants to use MATLAB because most of you are computer scientists. And you know, what the hell is this R thing? By the end, I convert almost everybody to R. So I'm pretty persuasive. And R is great because it's got so many built-in things for doing statistical things that you would have to write otherwise. And it's free. That's a pretty good selling point. MATLAB is really good at signal processing, but when it comes to other statistical stuff, I'm not sure there's as much stuff. Maybe there is, I just might not be familiar with it. I guess there might also be a few Python fans out there. So really, it's up to you. We don't care what you use, but R is great. So and if you need help with programming, I mean, like I don't know what you, Matt, what do you use to program?
more MATLAB, but
but at least you can get MATLAB help from, and probably Jeff knows MATLAB too, right? If you can ask a computing question, if it's not an R, I can't help you. And Brian probably knows both of them, I guess. But use whatever you want. Okay. So that's programming. There's a list, again, of the kind of topics. This may change if we change our minds about things, or perhaps you guys might have suggestions about topics to cover. So this is tentative. Today we'll start with a review, and then we'll start with non-parametric density estimation. And what we're doing this year is starting with a whole bunch of non-parametric stuff, which is a bit different than what we've done in the past. So non-parametric density estimation, non-parametric regression and classification, clustering, non-parametric Bayes, some foundational stuff, then switching over to convexity and optimization, graphical models, then back to theory. So when we get to this part, concentration of measure and minimaxity, those are both very theoretical topics. We used to start with those. And after a while, I started to realize that it's better to have some context before doing that stuff. So you know why you're doing it. So this year we're going to try doing that later, and then a few other assorted topics. But again, if there's something that you're dying to know, and you say, did you cover this or that, we're certainly open to suggestions. Keep an eye, though, on the course calendar, because the calendar does tell you what we're doing every class, and it tells you when everything is due. And if there's changes, of course, we update the web page as we go along. Any questions so far? So instead of a final exam, we have a final project. And the project is similar to what you would have done in 701, but a little bit different. It's a little bit methodological. This is supposed to be a more theoretical course. And so the idea is basically if you think of yourself as writing a review paper, a short review paper on a topic. So the idea is you're going to pick a topic. Let's say you're interested in support vector machines. And then your goal is to just find all the key papers about the theory and methodology of support vector machines. Find, or not all of them necessarily, but find a few important key papers and read them and understand them. And imagine you were going to go to a conference to get a talk to explain the highlights of support vector machines. And so that's what the paper will be. It'll be 8 pages summarizing what's known theoretically about this particular topic, what assumptions are behind it, and so on. It's not required that you do new theory. Okay? This is a course, this is not your thesis. So if you want to do new theory, that's a bonus, but it's not required for the project. It's just more like a review paper. But you want to demonstrate in the project that you've read and understand the material. And your options are to work by yourself or work in teams of 2. And there's a very specific outline of how the project should be written, which I think is on the website. Okay, there'll be an introduction and so on. But it's an 8-page max. It'll be like a NIPS paper. Same format as the NIPS. In fact, you download the NIPS style files. Use the NIPS style file. And what will happen is, on February 14th, you need to give us a 1-page proposal. There's not much to this. Okay, this is just showing us that you've thought about it, what you're going to do. So basically, this 1-page thing is going to have a title, the team members, which will be you or you and someone else, a description of what it is you want to study. Like I'm going to study reproducing kernel Hilbert spaces or something like that. And kind of a reading list. Here's the papers I'd like to focus. So it's just to show us that you have a plan for what you're going to do. And of course, feel free to talk to us or the TAs. Of course, if you want to know, is this a good thing to work on? Is this a good thing to think about? You can certainly talk to us about it. Then there'll be, on March 21st, a project report, which will now have basically a good introduction to what you've read so far and what remains to be done. Then the final report's due May 5th, but the really fun part is the last 2 classes, April 28th, 30th. We do these things. We've done this for several years now. It seems to be kind of fun. Sometimes some people call them 2-minute madness. Some people call them spotlights. There's different names for them. If you've been to some conferences that do this, where you get up and you get 2 minutes to describe everything you learned about that topic. So it's, and you get, I forget what you do, 1 or 2 slides, I don't remember what you do. You're allowed 1 slide, maybe 2 slides in 2 minutes. So you can't say much in 2 minutes. By the time you get up and say your name and start to point to the screen, a minute's already gone. So it's more like an advertisement, right? It's more like, here's what I worked on. In 5 bullets, here are the main points I learned. Like, oh, these things are consistent under these conditions, but there's counterexamples in this paper, and da-da-da. You know, just show that you studied this and make it sound really cool and interesting. So you have to think really carefully about how to present things because we're brutal. The TAs are going to sit there and take your slides, which they'll get ahead of time. And when your 2 minutes is up, they flip to the next person. So it's kind of like we have a hook and pull you off when 2 minutes are done, right? So we'll talk more about that when it gets closer to the end of the term. Okay. So that's just of course, Ryan, is there anything you need to add there? Matt or Jeff, do you think I left anything out? Okay. Now, are there any questions? No questions? Okay. Everything was perfectly clear and perfectly to your liking. That's how I want to read that. All right. Good. Great. Then we should go on. Now, you guys standing at the back, do you want seats? I think there are some open seats. If you want to squeeze in, there's one there, there's one there, there's one there. If you don't mind squeezing in, little rows there. There's also some chairs at the front. You might want to be the most comfortable, but I hate to see you stand up the whole time. All right. So I recognize that most of you will not have downloaded the notes yet because you didn't know to download the notes. So what I'm going to talk about right now is a quick review of everything you should know from 701 and 705 in about 20 minutes. So it's going to go fast. Don't freak out. The notes are up there, and it's just a reminder. Okay, I'm just trying to refresh your memory. You can always go back and look these things up. And don't write what I'm saying down, because just watch me instead. Because the notes are on. You can download them later if you don't have a computer with you right now. There's no need to write these down. And here we go. You ready? A whirlwind tour. So we're going to do a little bit of probability, statistics, regression, and classification. And I'm hoping, again, all of this is, you go, oh yeah, I remember that from that class, or I know how to look that up. Okay, I hope none of it should seem new. So let's start with a few things in probability. By the way, this is also a good chance to let us know what you did and did not cover in 701 and 705. I did look at what was there, but I could still have a misimpression of what you learned. So feel free to say, oh no, we didn't really cover that, or, you know. So convergence and probability, first thing. I'm positive if you took 705, that's one you did. So, X converges, so Xn is a sequence of random variables, and we use convergence probability a lot. It converges to a constant. I picked 0, but it could be some other constant. Probability. Remember what that means? It means that the distribution of Xn, whatever it is somehow getting more and more concentrated around 0. So technically, the probability that Xn is bigger than any epsilon is going to 0. And these are all as n goes to infinity. Which is just saying that you pick any interval, and the probability is getting more and more concentrated. And of course, it didn't have to be 0. We could have convergence to some other constant. It's often 0. So let's just test your memory. Does that imply that the mean of Xn goes to 0? Convergence is probably to 0. Does the mean go to 0? No. Why not? You know why? Because there could be a tiny little bit of mass out here. And you can take this little piece of mass and make it smaller and smaller and smaller, so that you're still accumulating most of the mass here, but if you keep making this little piece of mass go off to infinity, you can make the mean blow up. So remember, convergence of probability is not strong enough to imply convergence of the mean. All right. And this is often written in another notation. Now this part I'm not sure. Did you do this in, did you learn this notation? Xn is little op1. Did you do that some of them? Yes. So that's just another way of writing it. It just means Xn is small in probability. It's going to 0. All right. Good. So far, so good. The other main type of convergence, you probably learned that there's like many, many different types of convergence of random variables. Unlike calculus, where convergence is just convergence, in probability there was all kinds of different types, almost sure, improbability, blah, 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 blah. But really there's only two we make heavy use of, improbability, and the other one is convergence and distribution. So remember, what does convergence and distribution mean? It means Xn convergence and distribution. So we usually write that with like a squiggly arrow, or some people put a D for distribution in. It means that the distribution of this random variable converges to the distribution of this random variable. So it means that what is the distribution function? The distribution function is defined to be the probability that Xn is less than X. And you remember from 705 that the distribution function completely characterizes the distribution. All the information about the distribution is contained in the CDF. And so this means that this converges to this as n goes to infinity, but not at each x. Do you remember where it converges? At each point at which this is continuous. If there's a jump, we don't require convergence there. Technical reasons. But at each continuity point of this converges. So that just basically says that I can use this distribution as an approximation to this distribution. That's what that's really saying. Does convergence and distribution imply convergence probability? No. Good. Throw these little tests in there. See if what you remember. All right. The other piece of notation that I guess that you would have done would look like this. Big OP as opposed to little OP. You did that too? Yes? So it just means that, what it means is that Xn divided by An is bounded in probability. What does that mean? It means that if I do the distribution of this thing, it means it might wobble around it, but it doesn't shoot off to infinity. It kind of stabilizes. The probability doesn't take off. It can be tracked. In other words, if you give me any number, however small, let's say some small epsilon, I will find a point, that I call it M, M, such that eventually the probability in here stays at least 1 minus epsilon. You give me any epsilon, 0.0001, I'll find a big number, say minus 1,000 to 1,000, and I'll guarantee you that as long as n is large enough, the amount of probability in here stays to be at least 1 minus epsilon. So, roughly speaking, that's the probabilistic version of being bounded. When would that fail? That would fail if I had a distribution that looked like this, but as n got bigger, if the distribution moved off to the right, no matter where you put an interval, you could never trap the probability. So that would be something that's not bounded. Okay. All right. And the two very, very important theorems we learned about convergence, sort of crowning achievements of probability, were the weak law of large numbers and the central limit theorem. So remember how that works. Let me say actually a note about notation here. So whenever I write that, that means x1 to xn are samples from P. That means they're independent and identically distributed. Or, I don't know, there may be some times when we deviate from the independent, identically distributed assumption, but usually we don't. So the default assumption is, unless you say otherwise, assume everyone's independent and identically distributed. I don't want to keep saying it over and over. Okay, so when I write this, either a random draw from here, they're independent, identically distributed distribution. And in particular, let's suppose this has a mean. Why did I put xi in there? Because they all have the same mean. They're I, and b. So I put any I. I put 1. And then the law, what does the law of large numbers say? Well, it says if I take x bar, then x bar n converges in probability. So that was, we probably called that the weak law. Or written the other way, x bar n minus mu, little o p. Okay. Questions? It's all coming back? Good. Then let's go to the central limit theorem, the other biggie, which says that, let's now assume also that these guys have a finite variance. And remember, the central limit theorem says that root n x bar n minus mu converges to distribution. I'll divide mu by sigma. Converges to distribution to a normal 0, 1. Standard Gaussian. Pop question, pop test question. What if I replaced sigma with the sample standard deviation? What if I did this? Well, remember, this is just some people like to divide here by n minus 1. That doesn't matter, right? It's pretty much the same thing. What would happen if I divide by the sample standard deviation? Does this still go to a normal 0, 1? I got half yes and half no. Yes, it does. Anybody remember why? What theorem? The Slutsky's theorem, right? That I can rewrite this as Sn and multiply and divide by sigma. This is converging to this probability, so this is converging to 1 in probability. And so by Slutsky's theorem, if this is converging in distribution, this is converging in probability, the product converges in distribution. That is all of probability in 4 minutes. You probably also did a little bit of concentration, like filtering, inequality. We're going to come back to that later in the course when we talk about concentration measures. All right. Questions? Good, because the rule is if there's no questions, that means I'm going too slow and I double the pace every time. So now we're on to statistics. So in statistics, we often have some quantity we don't know, a parameter, like the mean of a distribution or the mean and variance. It might be a vector, like the mean and variance of a normal, some unknown quantity. And what you learned in 705 and 701, for that matter, was to come up with an estimator somehow. So we'll follow tradition here and usually put a hat on that to mean it's an estimator. I often write theta hat sub n, just to remind you that it's based on n observations. If we were more careful, I guess we would write it like this, to emphasize that it's a function of n data points, but we usually leave that off because it gets tedious. And you covered, I'm sure, this critical fact, which is the bias variance breakdown, which is that if I look at, if I say, look at the estimator, look at the true value we're trying to estimate, and say, what's the expected square difference? You learned that that can be written just with a few lines of algebra as the sum of two things. Let's say b squared plus b, where b is the bias. Mean of the estimator minus the true value, and v is just the variance. that's a very, very helpful thing because it allows us to study the error in these two separate components. And we'll see that, and I'm sure you've seen this before, that a lot of the algorithms in statistical machine learning involve lots of tuning parameters, and choosing those tuning parameters often involves kind of a tug of war between the bias and variance. If you want to make sure you don't have too much bias and too much variance. Okay, sticking with just simple parametric things like estimating a parameter, the most common method that you learn for estimating a parameter, actually let's spend a minute talking about parametric versus non-parametric models. So remember, a parametric model is something like this. You have a set of densities indexed by a parameter. So the notation I'm using might be a little bit different than is sometimes used in machine learning. This is actually worth pointing out. In machine learning, people often write this. If they write px, what they mean, well, I guess we do this in statistics too. It's a little bit ambiguous now that I'm saying it. But when I'm writing it like this, I don't mean theta as random. What I'm saying here is that I have a density function. I have a density function for x, but it depends on the parameter theta. And sometimes, just for short, I'll write that here. So I hope that's not confusing, but x is the random part, theta is just a parameter. So for example, in a normal distribution, theta would be mu and sigma. It's not random, it's the parameter. And a parametric model means you have a family of densities indexed by finitely many parameters, like a normal distribution. Whereas non-parametric, which we'll talk about in great detail, means it doesn't have a simple representation in terms of finitely many parameters. Effectively, there's infinitely many parameters. But sticking with the parametric case, the most common method of estimation is to form the likelihood function, which is the probability function, where now though we fix the data, we think of it as a function of the parameter. And if the data are IID, that just becomes the product. Is this a probability distribution for theta? No, this is just some function. The random part's x. This is a distribution for x. It integrates to 1 over x. It doesn't integrate over theta to 1. It might not even integrate over theta. This is just some function of fixing the data and thinking of it as a function of theta. And we maximize it. The MLE, the maximum likelihood estimator, is the maximizer. In fact, in practice, you were probably told to maximize the log likelihood. The likelihood and the log likelihood have to have a maximum at exactly the same point, right? Because log is monotonic. And it's usually easier to maximize the log likelihood. So you think of it as the maximizer of the likelihood or the log likelihood. And that's the most commonly used estimator in parametric inputs. Why? Why do we like that estimator? I know you know this. I'm sure we're so quiet in the first class.
Because it has a bunch of nice properties.
Thank you. That's it. It's got a bunch of nice properties. Yes, thank you. It's got always nice properties like it's asymptotic normal. And in particular, in a certain sense, it's optimal in some large sample sense that, again, I won't go into the details, but we did that in 705. Not always, however. Maximum likelihood, remember, can be a disaster. For example, in high-dimensional problems, which we'll talk a lot about in this class, we'll rarely use the maximum likelihood standard. Maximum likelihood tends to work well when you have a lot of data and not too many parameters. But when you get to the high-dimensional world, maximum likelihood doesn't work so good anymore. So we'll talk about that in detail. You probably, well, I know, not probably, you did learn this thing called Fisher information. Fisher information based on n observations. And it's an additive quantity, so you can think of that as the Fisher information of one observation times n. And what was that, it's something like minus the expected value of the derivative of the density, second derivative of the density. With a corresponding definition, when there's vector value parameters, you get a Fisher information matrix. Here I'm doing the scalar case, but it's just it's a scalar quantity. And the reason why that's an interesting quantity is because you learned that there was something like a central limit theorem for maximum likelihood estimates, which is the following: theta hat minus theta over its standard error converges to normal, where the standard error here is I guess I should write it like I did in the notes. And from that, what you did, the main purpose for doing this was you learned how to construct a confidence interval. Is that from this, you said if I take theta hat plus or minus z alpha over 2 times the standard error, remember that this is the number from a normal distribution that has probability alpha over 2 of the right tail. That this interval this interval is random. Why is it random? Well, because theta hat depends on the data. The data are random, theta hat's random, so this is a random interval. If I gave everybody in the class a different data set, everybody would get a different interval. And 95% of you would find out your interval tracked the true value. So you would see that the probability that theta is tracked in C actually converges to 1 minus alpha as n goes to infinity. But remember, when we write these statements, theta here is fixed, it's C that's random. It's a state, probability is going to look at procedure. So I'm sure you did that when you did confidence intervals. Questions? I'm going to have to double the speed again. All right. There we go. Pretty soon. I'm talking so fast. One thing that's going to come up, especially later in the course, although we'll mention it even at the outset, is this notion of minimaxity. And I know you did a little bit of this in 7.5, but not very much, probably. But we'll do it in detail later in the course. And what is minimaxity? It's a way of measuring how good estimators are and how difficult a problem is. And the reason why this is important is, suppose we have a problem, and I come up with an estimator. And this is a great estimator, and Matt comes up with an estimator and says, no, I got an estimator. My estimators, I like my estimator better. How are we going to compare them? How are we going to say who has the best estimator? Minimax theory provides one way, not the only way, but one way of saying, oh, this is the best you can possibly do in this problem. And so it works like this, is one starts with a loss function. A loss function you can think of as measuring, in some sense, the distance between someone's estimator and the truth. So an example, the most common example is square error. But it doesn't have to be square error. It can be anything. Now this is a random quantity, right? If I come up with some data, I get an estimator. This loss function, I can't really compute because I don't know the true value, but nonetheless, mathematically, it's a well-defined function. It's a function of theta. It also depends on the data. And we're interested in its average value. So that's the risk function. The risk is just the mean of this thing. So that's no longer random. It's a function of theta. So let's plot that. Here's theta. And I don't know the true value of theta, but what I can do is for every value of theta, I can say, what if this was the true value of theta? What would the expected loss be? What if this was the true value of theta? What would the expected loss be? And I can draw this function to know what it is. This depends, though, on which estimator I have. Say this is one estimator. Now, if Matt says, oh, here's my estimator, let's compute the risk function. So I take his his estimator. And at each value of theta, I ask, what is the expected loss of you see this? Maybe this function looks like this. Sorry, Matt. That wasn't a good one. It's like, you know, in this case, it's pretty clear. Mine's better. I beat them everywhere. Unfortunately, it's rarely the case that when you compare two estimators, that it's so obvious. More often, you might get something, oh, this one looks like this, and this function looks like this, and sometimes one's bigger, and sometimes the other one's bigger. And so one way to compare these things is to look at the worst case. We don't know theta, so let's look at the worst case over theta. So let's take the maximum risk. If we compare them by the maximum risk, this one has a high maximum risk, this one's, well, I didn't draw a good example, let me do this. This one has a high maximum risk, this one has a lower maximum risk. You want to find the estimator that has the smallest maximum risk. That's the minimax risk. The minimax risk is the smallest. The int, if you forget what int is, it's just minimum. The minimum over all possible estimators of the maximum risk. So that's the maximum sup or maximum over theta. So I have to imagine doing the following thing. How many estimators are there? Any function of the data is an estimator. So there's infinitely many estimators. So intuitively, you have to imagine, take any estimator, figure out its risk function that involves doing an integral at each value of theta, take the maximum over theta, and now do that over every possible estimator of the universe and minimize that. Well, that's not so obvious how to do that, right? So there's a lot of tricks that go into trying to figure out what is this minimax risk. It's not obvious by the computer. In 705, you may have done it for parametric models, but we're going to mostly do non-parametric models here. Later in the course, we'll talk in detail about how you actually compute this minimax risk. Computing this is important because it's a measure of how difficult this problem is. Some problems have very slow, or very large minimax risks. That's telling you it's a hard problem. Some of them have much smaller minimax risks. That's telling you it's an easier problem. And again, it's a way to check your estimator. If I have an estimator and I go, it achieves this risk, then you can't do any better than that. But if I have an estimator and it doesn't achieve this, that means there's still room for improvement. So this is a benchmark that's pretty important for net theory. So how to compute this and how to use it and so on will be something we'll talk about in detail. Okay. Questions? Yes.
Are we always interested in expected loss? Why is expectation so special that we always let risk be that?
We don't have to do that, so you can use, instead of expected value, you can talk about, some people look at the probability that the loss is bigger than some number, you want that to be small, so you can do probabilistic versions of it too. But the truth is, whatever you discover as a good estimator is probably still going to be, not much is going to change if you use the expected value, and the calculations are usually easier using the expected value. So a combination of simplicity, it's easy to compute means, and that it doesn't change much if you use quantiles and so on. You tend to use the mean. But you're right, you don't have to use the mean. You can talk about the median loss and so on. Any other questions? All right. So that finishes statistics. We just did 705 in 15 minutes. Let's see where we are here. We could have the whole course done by the end of the first lecture. Let's get started. Now let's talk about regression. By the way, I forgot to mention, so the course is called Statistical Machine Learning because machine learning and statistics used to be somewhat distinct fields, and over the years they've gotten more and more closer together to the point where it's hard to say where one starts and where one ends, and in fact, some would argue there isn't really much difference between the two fields. But there are some cultural differences, and I think one of them is this, that I'm about to do regression and then classification. Whereas I'll bet you in 701 they did classification and regression. Is that true? Because in machine learning, for certain grand historical, sociological reasons, classification is given a lot of attention. So, a lot of focus on classification. Regression, perhaps less so. And I think in statistics it's the reverse. Regression, for whatever reason, tends to usually get more focus, and classification is less focus. Did you agree with that, Ryan? Yeah, I think that's true. And it's probably just history about the types of problems statisticians worked on over the years, compared to when computer scientists started doing statistical things. They tended to be doing classification problems. So it just reflects the two different histories of the fields. Of course, they're highly related, and I am going to start with regression. So regression, remember, is this problem. I have a random vector, x, let's say it's in Rp. And then that's usually called, so in statistics we would say covariate. In ML, features. And then the y is sometimes called the response or the outcome, probably other names I'm forgetting. And of course, what distinguishes regression from classification is just that regression means y is real value, classification y is binary or discrete. So we're doing the continuous version first. And the goal is, given x, can I predict y? So x might be 5,000 genes that I've measured on you, and y is your blood pressure, and I want to predict your blood pressure from your gene measurements or something. Now, we already get back into this area, which by the way is called decision theory, because how you proceed from here depends on which loss function you pick. The most common loss function is squared error loss. So suppose I remember that I'm going to predict your y just from x. So I'm going to take your x and create some function. I'm going to take your x and do something to it and spit out a number. So m of x is going to be real value. And I want to compare that to your y value. And the most common way of measuring loss is squared error, but it's certainly not the only way. You could use lots of other loss functions. However, 95% of the time when people are doing this, they're using squared error, and we're going to use squared error unless we say otherwise. So the goal is to try to find some function of x that makes this prediction risk, did I give it a name? I just wrote out this one. So we'll call this the prediction risk small. You give me your x, I compute my function m, I spit out a real number. Now I measure your y, and I say how far away was it. Which function m minimizes this? Minimized by, right. The minimizer is the mean of y given x. So if this is if I draw it two-dimensionally, this is x and y. And if you imagine now, I have a two-dimensional distribution in this case. At each x, I can take a slice and get a distribution and take the mean on that slice, and eventually I'll get a curve. And that's, in some sense, my optimal predictor, at least under this loss function. Now when a person comes in and says, my x is here, then I know how to predict. I use m of x. Of course, we don't know this, right? Because to actually compute m of x, the regression function, as it's called, the mean of y given x, would require knowing the joint distribution. We don't know that. We're going to have to estimate this, right? That's what it's all about, is estimating this thing. Now, when we do non-parametric regression, we will try to estimate this regression function under very weak conditions. But the starting place is to say, well, let's first start off with simpler functions. Let's start off with linear functions. So remember that linear regression, we don't minimize that over all possible functions, that loss. We minimize it over linear functions. So I want to look at how small can I make my prediction error if I only use linear predictors. So what's a linear predictor loop like? It's going to look like this. Beta 0 is predicted equal to x. Squared. Notice that I'm not saying that the mean of y given x is linear. I'm not saying that the true regression function is linear. No matter what the true regression function is, I can still ask, what is the best linear predictor? What is the value of beta 0 and beta that minimizes this? Now, it's kind of annoying to always have to write beta 0 plus beta transpose x. So if we agree that when I write out x, some vector, what if I always put a 1 in the first spot? That would make beta 1 take the role of the intercept, right? And so I can just get rid of this and write this more simply. So I'm usually quite lazy and I do this, but you should understand that the intercept is the first term in there. This makes it easier to write. All right, so now we're asking a different question. We're saying, which vector beta, that is, which linear predictor minimizes that? So you can, the nice thing about that is, if you didn't do this in 705, here's a good homework exercise. Take the derivative with respect to beta and set equal to 0. This is not a hard problem. And you can figure out the optimal beta, although I got it wrong in the notes. That's Brian pointed out to me. So here's the correct answer. Well, I'll write it the same way, but I wrote here that sigma is the covariance. In the notes I said sigma is the covariance of x. That's only true if the x's have been standardized first. So sigma is really x transpose. Remember that x is a vector. So xx transpose is a matrix. And alpha is just the covariance between y and x1, y and x2, and so on. So so in principle, we can talk about the best linear predictor now. It's this function. Given somebody's x, I can plug it into that formula, and I get the best possible linear prediction. It minimizes the prediction error over all linear predictors. Now we still have a problem, because I don't really know these quantities. So what you probably learned to do was to estimate them from the data. So how does that work? So remember, what you do is you go, well, we have some data to start with. We don't have some data, we're in trouble, so we assume we have some data to start with. In ML, would be called training data, and pairs of observations. And this is useful because this will help us to estimate these quantities. So there's two ways to look at it. I can try to just replace these quantities now with their sample using the data. Or alternatively and equivalently, I can just take the expected value here in this loss function and replace it with its sample version, the training pair. And I can minimize the training error, and that's called least squares. So the least squares estimator, actually let me write it. This beta transpose. So the reason why I'm making these funny symbols is because I'm trying to distinguish between the random variable x versus a whole collection of variables. In particular, this guy is all of the x's strung together. Usually in statistics, we call this the design matrix. I don't know what it is. But it's what this is this is an n by d matrix. So each row is one person. I take each person and I take those features that are measured, and each row is one person. Or if you want to think of it this way, each column is one feature. This is feature 1 measured on n people, feature 2 measured on n people, so there's an odd name. And similarly, this funny y, I was just using to indicate the yn. And now that's it. You take the data, you form this matrix, this vector, you minimize the training error, and you get an estimate of the best linear predictor, which is the least squares estimator. Now there's some caveats here. I'm assuming that x transpose x inverse, x transpose x is invertible. That's another place where things change in high dimensions. If we have more features than people, this isn't going to work. That's why when we talk about regularization and so on later, apart from the least squares estimator. But you should really think of this as an estimator. This quantity. Okay. Everything okay? All right. I want to mention another useful fact, which may or may not have been mentioned in 701. If I take my estimate now, beta hat, and I apply it to the observed data. So if I could, I'll just draw one dimension. Here's my data. What we're doing is basically fitting a line. And now in each of the observed x's, I can ask what the actual value now is on that line. That's called the fitted value. So I can ask, what is y hat? Did I use 1 hat here? Which is, right, I'm just plugging the observed data back into my regression equation. So I'm saying if I used your training data, but if you give me your x back and you asked me to predict it, pretending I didn't know why, this would be the prediction. It's just the values on this plane, or this line in this case. So we call these the fitted values, the predicted values. And you notice now, if I look at this equation, x times beta hat, but if I take beta hat there and plug that in, I can rewrite this as h times y, where h is x transpose x inverse x transpose. So, did you do that at 701? This is called the hat matrix. This is good to know. So, this is useful because, first of all, it has we're going to see it has a natural generalization and non-parametric regression. So let me just say it again. After you've done all of this least square stuff, in the end you can think that we're taking y, we're hitting it with some matrix called a hat matrix, and getting out predicted by y hat. And the interesting thing about it is it has a geometric perspective. Because if you think about, I can't draw very well, but I'll try my best here. If I think of y, your set of y values, think about that as a point in Rn. You have n data points, you have a point in Rn. What we're really doing is projecting it onto a certain space, namely the space spanned by the columns of x. So let me elaborate on that. This matrix H is a projection matrix. What does that mean? It's symmetric and idempotent. H squared equals H. So it's projecting on some linear subspace. What is the linear subspace? It's nothing other than, if I think about these columns in the X matrix, those are just d different vectors. And think of all the linear combinations you could form from those B vectors. In other words, the linear span of the columns, or the column space. That's what we're projecting onto. And that's really what regression is, right? You're trying to approximate some sort of output of some lower dimensional subspace. And the hat matrix here is just projecting y onto y hat, which lives in this lower dimensional subspace. That's a geometric interpretation of what least squares regression is doing. So this little equation here, the predicted values of the hat matrix times y, you should verify that H is a projection matrix. And again, we'll see non-parametric generalizations of this. And here's an interesting feature about H to keep in mind. If I compute the trace of H, what's the trace? It's the sum of the diagonal elements of the matrix. The trace of H is D. It's sort of the number of degrees of freedom I'm using up to do this prediction. And again, we'll see generalizations of that later in the course. So for those of you who took 707 regression, you've seen this, but if your regression experience 701, you may not have.
Is it deep within high dimensional?
No, so everything here, I'm still in the low dimensional case. Yeah, good point. Everything changes for the high dimensional case. Okay, so that's the hat matrix. Just keep an eye on the time. We talked about the bias variance trade-off for estimating the parameter theta, and there's a similar bias variance trade-off for regression. Let's remind ourselves how that works. So, actually, I wrote it in the notes a little bit more generally than the linear regression. I said, suppose we have a regression model of the following form. Y is some function of x, which I'm going to leave to be pretty arbitrary now, and plus some error. So that's kind of the general version of the regression model. And suppose we have some sort of estimator, m hat. So in our linear case, m hat, in the linear case, m hat is just this. Later in the course, we'll have more general things. And that will, of course, give us given a new x, we can plug it into m and get the y hat. Then we have the following thing. If we look at the expected value of y hat minus y, now there are, after warning, there's different versions of this depending on what you're thinking of as being random. So this is the fully random version. What I mean by that is the training data are random, but you're also given a new random x, and then you make a prediction and we compare that to the person's y. So the new observation is random and the training data are random in this equation. So everything's random. This expected value is over all the randomness. And the bias variance equation actually has an extra term. It looks like this. Okay, so what are these three things? V of x is again the bias. V is the variance. And sigma squared is the variance of epsilon. So let's think about this for a second. At any given x, better. At any given x, we can talk about what the true value is of m of x. And then we have our estimator, which is a random function. Why is it random? Because it depends on the training data. And the training data are random. If I gave you a different training data set, the true m of x would stay the same, but your m of x would change. And at any given x, we can compare these, And there's a bias and there's a variance. So the bias is just the mean minus the truth, and the variance is just the variance of that. Where again, the variance means over the randomness of the training data. But then we're integrating it with respect to, whoops, there should be a density of x. That's reflecting the randomness of the new observation. And then there's one extra piece, which we call the irreducible error. Why is that there? This wasn't there when I did the theta hat minus theta. Where does that come from? It's because I'm trying to not estimate something but predict something. So if I'm trying to estimate a parameter, there's only a bias and variance. When I'm trying to predict a random variable, there's always going to be an extra source of error because even if I knew the true regression function, so there's no estimation error at all. When I go to predict your blood pressure, I'm going to make an error because your blood pressure isn't equal to m of x. It's equal to m of x plus some random error. That's the irreducible error. That's just, and you can't help that because you're trying to predict something random. In fact, a lot of people just ignore this. This is not anything we'll ever get rid of. These are the things we're going to try to make small, the bias and the variance. Training data, and you do give me an estimate of the regression function. Maybe a linear estimate, or maybe something else. And I want to know now, what is the risk? How well are you going to predict? How do we estimate the prediction risk? So the natural thing might be to use the training error. Is there any problem with just using the training error? Remember the training error of, say, in the linear case. Looks like that. Is that a good estimate of prediction risk? Why not? Right. We chose beta hat to minimize this. If we now use the same quantity, it's going to underestimate the true risk. Now, if the dimension here was small, so if there weren't many betas, and if the sample size were large, this wouldn't be a big issue, but it's going to start to become an issue when we do more complicated things, like higher dimensional problems or more non-parametric things. Just to give you a simple example of that, suppose my data set looks like this. Now you ask me to pick a regression estimator, and I do this one. There's my regression function. The training error is 0. But nobody thinks I'm likely to predict a future observation well. So you can see that when you're fitting to the data, there's the concern about overfitting in particular, and that the training error will be downward biased. So if we don't use the training error, what do we do? Well, there's a variety of different things we can use. The most common one being cross-validation. Remember, in cross-validation, roughly speaking, you use part of the data to construct your predictor, and then you use the rest of the data to estimate the prediction risk. And cross-validation comes in many different flavors, right? You could split it into 2. You could split it into 10 pieces. In linear regression, it's actually easy to just leave one out cross-validation. Did you do leave one out 7-1? Yeah. Okay, so remember, how does it work? You do this. You leave one out, cross-validation risk estimator. Looks like this. I take each observation, and now I produce, I'm going to call it actually, so in principle, here's what I do. I take the first pair of observations and I drop them on the analysis. I pretend they don't exist. I fit the linear regression. I get beta hat. and then I get the predicted value. Right, so the first pair is gone, x1, y1 are gone. I have to compute beta hat, which we can call beta hat minus 1. And then I can get my predicted value, 1 hat minus 1. And that's supposed to take away the bias. Well, it does take away the bias from fitting and estimating risk from the same data. And now I do that for the second observation, the third observation, the fourth observation, and so on. And this, it can be shown as an almost unbiased estimator of risk. It doesn't self-compute that down unbiased. Now, it would be really painful to actually compute it the way I just described it, but I hope they taught you in Seminar 1 that you don't ever compute it this way. Right? There's a shortcut formula. Did you do the shortcut formula? Oh my God. Okay. Well, you either didn't learn it or you've forgotten it. Either way, it's a tragedy. So let's say the shortcut. The shortcut is very simple. This is equal to the following thing. You probably remember it when you see it. So what is this? This is yi. This is just yi hat without dropping anything out. Oh, question.
Why do you call that an almost unbiased estimator?
Well, because it's actually based, it's actually estimating the risk for n minus 1 observations, not n. So it's actually estimating r sub n minus 1 instead of rn, because you're using n minus 1 observations. But that is a very small factor. Okay, so we have this equation which says just take the fitted values without doing any dropping out. So in other words, if I covered this up, this would be the training error. What am I dividing by? Ah, there's our hat matrix. You just take 1 minus the diagonal of the hat matrix. And this is not an approximation, this is an identity. So this is just a computational shortcut. You can do leave one out cross-validation without ever leaving one out. You don't actually have to do that, it's more of a conceptual thing. So that's a good trick to know. And in fact, we can do even a bit better than that. Because often what people do is they say, well, look, this is the hat matrix. Just remember what this is the hat matrix over here. It's some n by n matrix. And we're pulling off these diagonal values. What if I just take the average of those values instead and replace each HII with its average? That will simplify things even further because this now becomes a constant and I can pull this up front. But what is the average? What is the average of those values? Yeah, it's the trace, it's the trace, sum over n, but the trace we saw was just the number of parameters over n. So that is this, I'm going to write it like an approximation. That gives us 1 over 1 minus e over n squared times, and what's left over is 1 over n times this, which is just the training error. That's r hat. This is usually called GCV, generalized cross-validation, although I always say it should be called approximate cross-validation, but anyway, it's called generalized cross-validation. So that's another way of estimating the risk. In practice, they often give very similar things. And the nice thing is it kind of shows you how the complexity of the model comes in, right? So when I add more parameters, if I add more covariates, the training error is going to go down. But D, the number of covariates is going to increase, and that's going to blow this up. So you can see how the complexity of the model is entering into it. And we can even go a step further. Another common thing to do is to now do a second order Taylor series expansion of this. And if you do that, you get the following formula. You get, it's just the training error plus 2d, I'm going to write it like this, where sigma hat squared is actually the same thing. 1 over n. Actually, what is it? Is it 1 over n? This is sometimes called mallow CP statistic, or it's essentially the same, what's sometimes called AIC. And again, it has a really nice interpretation because this is the training error, and this is like a complexity penalty. If I add more covariates to the model, we'll talk about this in great detail later. Of course, the training error goes down, we start to overfit, but the complexity goes up. So this has like a penalized training error. The nice thing is I like to think of them as all linked this way. The starting thing is kind of cross-validation. Then you can approximate it once to get generalized cross-validation. Then you can approximate it again to get CP or AIC. They're all kind of doing the same thing.
So, historically, is there a relation between this lasso?
The lasso we're about to get to right now.
Like, because when we study lasso, like we also study AIC or BIC. So before lasso it was AIC. So is there a historical significance that from this lasso came or something?
Well, so that's an interesting question. Yeah, in the old days, what we used to do to try to, we're getting a bit ahead of ourselves, but we used to looking at subsets of the variables because we had too many variables, and we would compute something like CP or CV and try to find the minimum risk. But that was a combinatorial search. And the lasso gets rid of the combinatorial search. But as we'll see, so Ryan happens to be an expert on this, and in particular, Ryan will talk about at some point, there's a notion of degrees of freedom for lasso, which is pretty cool. And so it all kind of comes together later on. So yeah, we'll get to that. That's all very important. For now, I'm just think of it as I'm talking about some fixed problem with a fixed set of covariates. We're not doing any variable selection. Well, actually, the next thing to notice is high dimensional. We're going to touch on it now. My goal here is just to, I have like half a page on high dimensional regression because I just wanted to talk about now the parts you would have seen in 701. And then we're going to have entire lectures later in the course about the lasso related method in detail. But this is just to remind you of what you probably already know, which is that when D is bigger than N, you can't do least squares. You get a useless estimate. Or even if D isn't bigger than N, but it's big, the least squares estimator has a very high variance. And so we need some way of dealing with it. And so what we'll see later in the course is there's a variety of ways of doing it. The older fashioned way was to do variable selection. So just to be concrete, let's suppose I have 100 people. So N is 100. But I've measured 5,000 genes in everybody, so D is 5,000. So the least squares estimator that. When I was a student and we did regression, what we learned to do was subset selection. We tried to find a small subset, well, we didn't measure genes in those days, but whatever the features were. You tried to look for a small subset of them that would predict well, and you literally just started searching over them. I mean, it was kind of chaotic. And the problem is, you have a lot of problems. One of them is computational. Searching over every possible subset of these things, there's 2 to the D possible subsets. Computational, that's impossible. But the other thing is, for every one of those, you have to estimate the risk and try to minimize it, so it gets very complicated. And so what we'll focus on mostly in this course later on are regularized versions of regression instead. The older one is called ridge regression. And I'm assuming you did both ridge and lasso in 701. So ridge regression, remember, you take the training error. If we try to minimize this, we try to get back to the squares, which is a disaster for the large regression. So we add this regularization term, and then ridge, it looks like this. You did ridge, right? L2, yeah. And you can see that as I make lambda bigger, I'm putting more and more of a penalty for using big betas. So when lambda goes to infinity, that would force me to take beta height over 0. And when lambda has 0, you get back to these squares estimated. In fact, one nice thing about ridge regression is you can write the estimator in closed form. It's just like the least squares estimator, except for this extra term. before you invert it, you add lambda times the identity. And you have to choose how much regularization to do. How do you choose that? Cross-validation. These same formulas still apply. That is, well, not all of them. This is still perfectly well defined, and this is also well defined with the matrix H changes. And what you get is an estimate of the risk. So the risk might look something like this, your estimated risk, and then you would pick the amount of regularization by minimizing the estimated risk. When we do regression, we'll go into detail about that. And for many years, people liked Ridge because, well, there wasn't many other things to use. The problem with Ridge regression, though, is this beta hat, none of the beta hats are ever 0. And so it's not really doing variable selection. So we always have this quandary in statistics. We'd like to do variables. We'd like to really find 20 genes that really predict well. That means you really want to make most of the beta 0. But Ridge regression is easy to compute, but it doesn't make them 0. And so what you did in 701 was you either called it the lasso or L1 regression, which was to replace that penalty with an L1 penalty. And as Ryan will explain in great detail when we do it in class, when we do it in the lecture, all kinds of magic stuff happens. There's something special about L1. But the important thing to note is that minimizing that beta, minimizing that thing over beta is a convex problem, so it can be done quickly. And it has the very nice property that the resulting beta hat is sparse. Many of the betas are 0. So it's doing variable selection for us without having to search for the variables. And there is a notion of, we'll see, effective degrees of freedom for the lasso that extends nicely from the linear regression case. So there's a lot of properties of the lasso, and we'll talk about all of that in detail later in the course. All right, what is the time? I'm over. So I usually am very good about finishing on time. I'm 2 minutes over. I'll see you on Wednesday.